So this is another lottery question. We did a lottery question in the previous lesson on the hypergeometric distribution. In this one, although it involves a lottery, we don't need to use the hypergeometric distribution because they've already given us the frequency distribution for the number of prizes here in this table. Well, they haven't given us the entire frequency distribution. They've left out a little bit of it, which we're going to work out as we go along. But let's take a look at the question here. A lottery collected $66,227,391 by selling tickets at $1.50 each. The prizes were as given in the table here. We want to find what is the probability of winning a prize and what is the expected return from buying a ticket. We can calculate the probability of winning a prize by using our standard formula for probability. Probability of a prize is going to be the number of ways that you can win a prize divided by the number of things in our sample space. The number of things in our sample space is going to be the total number of tickets sold. So NS equals number of tickets. They don't tell us how many total tickets were sold, but they tell us the total amount of money that was raised, the 66 million and change, and how much they sold each ticket for. So if we assume that all that money was raised by selling tickets, we can figure out the number of tickets through simple division. We're going to take 66,227,391 and divide it by $1.50 per ticket. And when we do that, we end up with 44,151,594. So that's how many tickets they sold. The next piece of information we need is the number of prizes. So they tell us the value of all of the prizes in the table and the number at each value. So if we want the number of prizes, I guess I just said number of prizes below, so I'll stick with that notation. The number of prizes, we just need to add up all of these numbers in here. So we punch all of this into our calculator and we find that the total number of prizes is 625,515. Now that seems like an awful lot of prizes. You might look at this and think, oh, I've got a pretty good chance of winning. And when they've given us the frequency distribution in the table, they've done it in a way that makes it look like there are a whole lot of prizes. But there's another possible prize that you could win, and that would be the prize of winning $0. If we want to figure out the number of $0 prizes, we have to take the total number of tickets sold and subtract off the number of prizes. So the number of ways that you can win $0 is going to be this 4,151,594 minus 625,515 gives us 43,526,079. So this category of people winning $0 is by far the most numerous category of prizes that are going to be awarded if we think of $0 as being a prize. So adding that final line to our table completes our frequency distribution, because now we've considered all of the possible events that can happen from buying a ticket. Back to our original question here, what is the probability of winning a prize? Well, we know now that the number of prizes is 625,515. We know that the number of tickets is 44,151,594. So our probability here, punching this into our calculator, is approximately equal to 0.01416, or about 1.4%. Which means, by subtraction, that 98.6% of the people who buy a ticket do not win a prize, or rather they win a prize that has a value of $0. The second part of our question here is, what is the expected return from buying a ticket? So remember, expected value means if you were to perform this experiment over and over again, buy a ticket over and over again, on average, how much money would you get as a return from buying each ticket? So this relies on sort of understanding what we mean by expected value. Our expected value in this case, and we kind of have to think of this as a weighted average. We are going to sum up all of the prizes, the values of all of these prizes, and we're going to multiply by the probability of winning that particular prize. So as we're doing this, we can neglect the zero prize because its prize value is going to be zero, so it's not going to contribute to our sum. But for the rest of them, we're going to have, let's see, our jackpot of $24 million times the probability of it. There's one jackpot winner, and there are 44,151,594 possible tickets. To this, we have to add our next prize of $100,000, again, times how many $100,000 prizes were there? There were 14. So 14 over 44,151,594 plus our next prize, which was $1,000. How many $1,000 prizes were there? There were 500. Again, divide this by 44,151,594. Our next prize was a $100 prize, and there were 25,000 of those. Again, probability, we divide by 151,594, and so on. We've got a $25 prize. How many of them were there? There were 100,000. 44,151,594. And finally, our smallest prize was $10. There were 500,000 of them over 4,151,594. And we could, of course, include the $0 prize, but the probability of winning that had by far the largest probability, 43,526,079 divided by 44,151,594. But of course, because we're multiplying by 0, this term is just going to go away. So a lot of times we wouldn't even write that down. So a lot of calculator work here, but when we work it all out, we get 0.813. So this is in dollars. So if we were to play over and over and over and over again, average return on one ticket would be about 81 cents. So you buy a ticket for $1.50, you expect to get on average about 81 cents return. So you're really expecting to lose about 70 cents every time you buy a ticket.